Oh, yeah, thanks for the introduction. It's great to be here. I love types, my favorite conference at all time. So this is why I'm back again with more simplicial type theory. Okay, so last year at TYPES, I also spoke about simplicial type theory, and I gave a motivation in terms of how hard it is to solve the coherence problem, and we need to solve the coherence problem in univalent foundations. And one aspect of which we heard about earlier, about constructing the type of semi-simplicial types, and you can use that to define the type of infinity one categories and do infinity one category theory, which is something we would definitely like to do because at least I belong to the tribe where we have become we take the higher types pill, but you can also motivate directed type simplicial type theory in other ways. You can forget about the homotopy aspect and say, well, we would like to have some synthetic theory of categories, some type theory where the basic objects are categories, because then you get a lot of free theorems. You get naturality, functoriality for free, and we like that in programming as well. So we heard Connor and others talk about. But so directed type theory is in the air, especially this year. But it's a bit hard to agree on exactly what the judgmental framework and should be. Should you have judgments for two-sided discrete fibrations, for fibrations, co-fibrations, for maybe Condorcet fibrations? There are many choices, and it's a bit it's still work in progress to come up with a good solution. So simplicial type theory offers you a bargain. You can do something like directed type theory today with all the free theorems, naturality for free, functoriality for free. It's very easy. You can do it in ordinary type theory, mostly. Some conditions apply. And the only thing you have to do is you have to prove a few propositions now and again. So it seems like a small price for working in a type theory you can have today. Okay, so how does it work? So Riehl and Schulman introduced this idea. They've introduced actually a more computational version, but a very simple version of it can be introduced by just adding to type theory an interval type. So it's a set, a type that is a homotopy set, has 0 and 1, a total order, and that is your co-representing morphism. It's the free-living morphism, and you get your morphisms in any other type by looking at the functions from the interval to your type. Great. And then to know that any function is a functor, you just compose. You have your arrow in x, and you have a function from x to y. You compose them, you get the image of that arrow in y. Right, so the thing that you have to prove some few propositions is not every type is going to be a category like this. You could glue together two copies of your interval, and then you're not guaranteed to have a composite of those two arrows. But you can look at the types that are categories, and those are called Siegel types. And those are the types which believe that any composable pair of arrows have a unique composite. And then if you like actual univalent categories and not just these pre-categories, you introduce another proposition about your type to say you want a RESC completeness condition, which basically says that the invertible arrows are the same as the paths in your type. Okay, and to illustrate how nice and easy it is to do category theory in this framework, we can define a coherent version of adjunctions of infinity categories, which otherwise may be a scary concept, by saying two functions f and g between categories form an adjoint pair. If you're given this pi type, which gives you the equivalences between hom types, and then because this pi type implicitly quantifies overall not just the objects of your categories, but also the arrows and the composable arrows and so on, then you get a coherent notion of an adjunction. It's very easy and concrete to work with, something you can get your hands on. Yeah, so the idea is that we represent our categories as simplicial objects via their simplicial nerve. So a category remembers not just its type of objects, but also its type of arrows, the type of composable arrows, the type of n-types composable arrows, and so on. And that's a nice way of organize the otherwise intractable problem of making coherent higher category theory. Okay, so that's the short introduction to simplicial type theory. Okay, so now let's talk about a few of the developments that's been since this was introduced. So my co-author, Jonathan Weinberger, and I, we started to do some fibered category theory, again, in the basic setup of Riehl and Schulman. And Cesar Badomiano Martinez studied co-limits and exponential functions. There's a prototype proof of systems by Nikolai Kudasov. And in that, there's a formalization of a vibrational version of the unit lemma that was already in the original paper by Riehl and Schulman. Okay, so one thing about just the basic setup where you have type theory and you've added this interval is that there are not very many categories around. So to get some actual to get your hands on some categories, you want to have at least the directed univalent universe of spaces or sets or homotopified sets, if you like. And there are two ways of getting those. So it's clear that what should be the so if you have the simplices, you want to know what are the maps from the simplex to the universe of spaces. Well, it's going to be ordinary discrete types with functions between them. And that can be represented in a vibrational way by, say, right vibrations or left vibrations or something like that. So if you want to do the LOPS construction, that gives you a way of constructing a universe that has that universal property. And there are two developments to put that into simplicial type theory. One, you do Dan DeCata and Matthew Weaver, and detailed in Weaver's PhD thesis from last year. And that is a bicubical setup where you really want to make a constructive version. So you look at cubical type theory and you look at simplicial type theory and you put them together. So you have two cubical directions. One direction is for where the cubical direction is spatial and one direction where it's categorical. And then you have some chance of making things computational. They don't quite manage to do it, and it's quite complicated. You have to integrate some of these cobar constructions as well. So with my co-authors, Jonathan and also Daniel Gratzer, we gave another approach where we work more axiomatically. So just looked at simplicial type theory, but added some modalities. And so in order to do this LOPS construction, you need an amazing right adjoint to exponentiating by the interval. I talked about that last time, so I'm not going to say so much about it here. But the main thing is you can get a lot of mileage out of going to kind of cubical version, and then you can carve out the simplicial objects as a modality. And then if you use Ingo Blechschmidt's the duality axiom, you can prove everything you want. You can prove that the universe you get is directed univalent. And if you add some cohesion style axioms as well, you also get many other things you need about this universe of spaces, and you can get structure identity principles in a directed way. So if you write down naively what should be the type of ordinary groups, you get that the homomorphisms of those, the arrows in the type of groups, is the group homomorphisms and so on. So the next step was we have a paper at LIX about the usual Uneda lemma, where you look at not just the vibrational version, but also when you have an actual Uneda embedding in a pre-sheaf category, and talk about co-complete categories and Khan extensions. And that was accepted for LIX, and Jonathan will talk about that next month in Singapore. So today I'm going to talk about some more recent work, even more recent work, is work in progress, about various decompositions of co-completeness and applications to synthetic stable homotopy theory. Okay, let's go. So one thing you'd like to do is you might like to decompose your co-limits into some smaller classes. So actually, I put this in the abstract, but not on the slide. So in classical mathematics, you can decompose co-limits as co-limits over groupoids and push-outs. And that seems to only work if you are a little bit classical. So if you have crisp excluded middle, so excluded middle for crisp propositions. So I'm not going to put it on the slides because I like to be constructive while I'm here and talk about stuff. So let's not do that today. So a couple of other decompositions of co-limits is you can decompose co-limits as finite coproducts and sifted co-limits. So what's a sifted co-limit? It's a co-limit over a sifted category where a category is sifted if the co-limit functor into spaces preserves finite products. So you get a commutation relation between finite products and sifted co-limits. And then, so here you see, we have to introduce this crisp notation. This is the epsilon of modal type theory you have to do when you do simplicial type theory, but it's very natural when you're doing category theory. You often have to do some arguments object-wise. Not everything is functorial, so it's a small price to pay to have this little bit of modal type theory in there. Right, so you can prove that a crisp category is sifted if and only if the diagonal map into all the finite powers is right cofinal. The right cofinal is my preferred name for the left orthogonal class to the right fibrations, but it's what generalizes to categories the notion of a cofinal map of posets. So if you have to take the co-limit, you can do it over a cofinal subclass, but in category theory, you do that restricting along a functor. And that I call right cofinal. So right because the arrow points to the right in the co-limit symbol when you write it like this. Okay, so then it's not too hard to prove that if a category has finite coproducts and sifted colimits, then it is in fact co-complete. And you can also show that you have some examples of sifted categories. For instance, the opposite of the simplex category is sifted. So geometric realizations are an example of sifted colimits. Okay. Harder is, but also very useful, is the decomposition of colimits in terms of finite colimits, not finite coproducts, but finite colimits and filtered colimits. What's a filtered colimits? It's colimit over a filtered category where a category is filtered. If whenever you have a finite diagram, you can extend it to a cocone. So you maybe want to define it like this. So there are two notions. One is say a crisp category is filtered if the co-limit functor preserves finite limits. Then it's hard to show that you have some examples. So it's maybe nicer to look at these weakly filtered categories. These are categories for which the diagonal functor into the categories, into the category diagrams for finite indexing set is right cofinal. Then it's easy to see that filtered categories are weakly filtered, but it was very tricky to come up with the converse. In classical mathematics, it seems to be a quite classical argument, and you can do it in the truncated world of one categories constructively, but it's kind of annoying. Luckily, Christian Sattler and David Wern came up with a very beautiful foundation agnostic argument that just works almost word for word in simplicial type theory. So that's great. Thanks so much for that. And then we can, once you have that, then it's not too hard to show that if a category has finite and filtered colimits, then it's co-complete. Okay, so now let's put that theory into use. So in stable homotopy theory, you look at the phenomena that remain once you take sufficiently many suspensions. So suspending a type is like making it a bit more like an abelian group. So in a sense, you're replacing your types by some free, you freely make them into symmetric infinity groups. So that's something you may have seen in the Freudenthal suspension theorem, which is treated also in the hot book. So homotopy theory is hard, and stable homotopy theory is slightly easier because it's a bit like linear algebra. You can start adding things a lot. Okay, so the category of spectra is something that you can define in hot as least the type of objects of it. But in simplicial type theory, you can now define it as a category by taking this limit in the simplicial types and showing that it is a category. So then the trick is you want to know that this is a co-complete category. And it's easier to show by the definition that it's closed under finite limits and filtered co-limits. So if we only knew that we also had finite co-limits, then we could apply the theorem and get that it's co-complete. Okay, there's an argument by Sebastian Knossen that does this. I'm going to skip over this and get to the conclusion because Tom is standing up. Right, so so one thing you can do is you can use the directed univalence axiom to lift the definition of smash product on pointed types to a functor on spectra. As first as a functor on pointed types, and then you can use that to define the smash product functor on spectra. That's very useful for doing stuff in synthetic homotopy theory, but we haven't really put that to use yet, but we just observed so far that it works. Let me skip this stuff about animation and just go to the next steps. So what's next for simplicial type theory? Well, we have the directed univariate universe of types. That's all very good. But lots of constructions to do, monads, monoidal categories, operats, and stuff like that, really needs the full category of categories, or the infinity one category of infinity one categories. So that's something we're working on. Then once you have that, you can do a lot of things, do some higher topos theory. It might be fun to do some meta theory of type theory internal to simplicial type theory, because now it can start to eat itself. We can also try to connect it to directed type theories by giving interpretations of various directed type theory in simplicial type theory. Hopefully, you can come up with a computational version of it and do some meta theory of simplicial type theory, do more formalizations, et cetera, et cetera. Okay, I better stop now.